This lecture entitled Here's the Chemistry, the Cause of and Solution to All of Your Problems is going to introduce the idea of solutions, molarity, concentration, and those sorts of things. The quote that we have is Everything is a miracle. It is a miracle that one does not dissolve in one's bath like a lump of sugar by Pablo Picasso. And Picasso was a great man, but he did not quite understand the solubility rules. So we'll see. The goals are that you be able to determine whether or not a substance will dissolve, and if so, by how much, and that you be able to express concentration in terms of molarity and molality. We want you to be able to describe conceptually what happens what will affect the solubility of a substance. So, what will make it dissolve more, what will make it dissolve less, and we want you to be able to write a solubility expression. So, here's what we already knew. You already knew that we can express the number of molecules in moles. And the reason why we do that is because there are a whole bunch of molecules in a solution or in whatever. So we express it in terms of moles. We also know that molecules need to be able to physically interact in order to do a chemical reaction. And we also know that molecules can be classified as ionic, polar covalent, or nonpolar covalent based on the electronegativity. So if you have an electronegativity difference that's large, it'll be an ionic. Okay, so this has a large electronegativity change. Okay, this one, nonpolar covalent, has basically a zero change in electronegativity. Okay, so that's stuff we already knew. It's stuff we learned earlier this year. Now let's take a look at what we learned in the lab. In the lab, you should have learned that solvents dissolve a solute to make a solution. I know that you can try saying that 5 times fast. But the solvent is what you dissolve it into. So it's generally the liquid in our case. And the solute is what you're pouring in. So it could be salt, could be sugar, could be lots of different things. And then the solution is the combination of the solute and the solvent. Solvents will dissolve in different solutes. Or excuse me, solvents will dissolve different solutes. So if you were to take salt and put it in water, it'll dissolve. But if you were to put salt in gasoline, it doesn't work as well. So one of the measures of concentration or how much stuff is in something was called molarity or moles per liter. So that's what we learned in the lab. So now let's take a look at solutions. Solutions are a combination of two different substances. Another way of saying is that it is a homogeneous mixture. Homogeneous means it's equally spread throughout the solution. Okay, so the solute is everywhere. There's solute here, and it's all in equal amounts. Okay, it's not a very good drawing for showing equal amounts, but it's equal amounts. But because it's a solution, it does not mean that it's chemically reactive. It means it can still be physically separated. A lot of the times we physically separate them by diluting, or excuse me, by decanting off the solution and the solid remains, or you can run it through a filter, generally speaking. Examples of solutions include Dr. Pepper. Dr. Pepper has, carbon dioxide that's dissolved in it. You have Kool-Aid. Kool-Aid has sugar dissolved in it. Salt water has salt dissolved in it. And even air is considered a solution because the oxygen is actually mixed with the nitrogen gas, which is what the predominant thing is. So you have solutions. And so you see the thing there. Why are chemists great for solving problems? Because they have all the solutions. A solute is a substance that is dissolved into another. Okay, you can have a solid, a liquid, or a gas solute, but you have to be able to mix it with a solvent in order for it to be a solute. So here you see an example of sugar cubes. Sugar cubes are actually a great solute because you can mix them in tea or Kool-Aid or whatever. So solutes are anything that will be able to dissolve in the solvent. A solvent is a substance that will dissolve a solute. So it seems like we're defining one with the other, and we kind of are at this point. But a solvent is basically anything that will dissolve whatever you're trying to dissolve. Now, generally speaking, we don't accept solids as a solvent because we don't really do that. You may get to the point where it's not really reacting. So you could, if you look at something like an alloy, but we're not going to do that. We're going to say for now that solvents are liquids or gases. And more commonly, it's going to be liquids. Now, the rule generally for solutes and solvents is that like dissolves like. A polar solvent will dissolve polar and ionic solutes because polar means you have positive and negative charges that are in there. And they could be partial, they could be small, they could be big. But basically, it's going to say that you have these positive and negative charges, and they are going to dissolve things that are positive and negative and positive and negative. Because the negatives will be attracted to the positives because of Coulomb's law, and the positives will be attracted to the negatives because of Coulomb's law. And if you're thinking, what's Coulomb's law? Remember, Coulomb's law was just the statement that opposite charges attract. An example of a polar solvent is water. Water has a partial positive and a partial negative. The hydrogens are positive, the oxygen is negative, and because of that, it's a polar solvent. Acids are generally considered to be polar solvents as well. There's a bunch of different ones that you could look at, but mainly we're going to stick with water. Nonpolar solvents will dissolve nonpolar solutes. And examples of nonpolar things are anything in which the electronegativity difference is very small, for something like gasoline or ether or something like that. Okay, what you see here is you see what happens when you try and dissolve oil in water. Oil is nonpolar. Water is polar, and if you look, the two just don't mix. So that's where the term like dissolve like comes from. Now we came up with this idea of the solubility chart, and we're like, hey, all these things are gonna not soluble means there's none in solution, and you have to qualify that a little bit. Everything to some degree is soluble. And by insoluble, what we really mean is not very much dissolves, but some does. If you were to take a little bit of barium chromate or barium dichromate, if you were to put just a tiny amount in a whole lot of water, it would dissolve, but just a little bit. So we're going to look at this a little bit later as far as how much is really a lot and how much is not. But for now, let's look at a nutrition label. It says you have a nutrition label for a Coke. It says name the solutes and the solvent based on the label. Okay, the first thing that you would look at is you look at the fact that you have carbonated water. Carbonated water indicates that you have water. But the carbonated indicates that you have dissolved CO2 in there. So which one is the solute and which one is the solvent? Well, you're taking CO2 and you're putting it in the water. So that makes water the solvent. And it makes the CO2 a solute. And so this would be true of any sort of carbonated beverages, whether it's carbonated water, Dr. Pepper, any of those sorts of things. You're going to have carbonated water. You have CO2, which is carbon dioxide, which is dissolved into the solution. Anything else that is here would be classified as a solvent. Oh, excuse me, a solute. A solute, because you're dissolving it in the water. So all of those would be acceptable answers for solute in addition to carbon dioxide. In this one, it says one particular brand of antifreeze consists of 50% water and 50% ethylene glycol. Name the solute and solvent for this solution. So this is kind of one of those tricky ones because generally speaking, there is more solvent and there is less solute. But it gets kind of tricky when you have a 50-50. Generally speaking, whenever you have a 50-50, you go with water. You would say that the ethylene glycol is dissolved in the water, even though technically neither is correct. In this one, it says water is often called the universal solvent. Why is this the case, and why is it not true? Water is very, very good at dissolving things. Its unique kind of structure, the whole partial positives and partial negatives, means that it can dissolve lots of different substances. It can dissolve, polar, ionic. It can, to some degree, dissolve some nonpolar based on when it interacts. But it's not a universal solvent. There's no such thing as a universal solvent because you're not going to be able to get things like oil to dissolve in water. It's just not going to happen. All right, so now we're going to take a look at concentration. Now, concentration can be thought of as the density of material in solution. So if you look, here I have the same number of particles. I've got, however many particles this is and however many particles this is. But the particles are a lot closer together here, and they're a lot more spread out here. So because of this solution is considered to be more dense, and this is going to be less dense. Okay, because of that, what we can say is this one is more concentrated, is the term we tend to use. And this one is more dilute. Even though they have the same number of particles, it's just talking about the relative space that the particles occupy. So now just because you have a lot of particles doesn't mean it's concentrated. And just because you have very few particles does not mean that it's dilute. Instead, you have to look at the ratio of the two. And generally speaking, when we look at the ratio, we look at something called molarity. Molarity is the most common measurement of concentration, and what it is molarity is moles of solute divided by liters of solution. We've already spent lots and lots of time looking at moles. We've spent lots and lots of time looking at liters. So really the only thing that's new is this term, this M, this molarity. And generally speaking, we express molarity in moles per liter, but we don't ever write out moles per liter. Instead, what we write out is M. Capital M indicates moles per liter. There is a way to directly measure molarity, or there's no way to directly measure molarity. There's lots of ways that you can do it though, and we'll explain that in the next video. But it is generally calculated. You can count moles. It's not really feasible, but you can, and then you can measure volume in a volumetric flask. So we've experienced a lot of that stuff. So really, the only thing that's new here is molarity. You also have molality, and here's why people get these confused. They sound very similar. You have molarity and molality. What's the difference besides a letter? Well, the biggest difference is the fact that you have moles of solute divided by kilograms of solvent. So the only difference is this one letter and then what you're dividing by. One's in liters and one's in kilograms. But you do need to know how to do the difference between the two. Sometimes it makes more sense to do kilograms as opposed to liters, especially when you have a situation in which you're increasing the temperature or something and the volume is changing as a result. Sometimes it makes more sense to use molality. Now, molality is just moles of solute divided by kilograms. Instead of expressing it as a capital M, okay, we don't do capital M, we do a lowercase m. That indicates the molality, which is moles per kilogram. So if we look at this first example, it says many textbooks state that the molarity of a substance equals the molality composed of water, if the solvent is water. Find the temperature for which this is true. Okay, so what you have here is you have the density of a solution, and the density of the solution is, it looks like the maximum density is like 9, let's say 999 point, let's say 98 kilograms per meter cubed. Okay, so if we have that as our density, we should be able to convert this thing into where we can find a relationship between kilograms and liters. So if I have 998 or 999.98 kilograms per meter cubed, I need to be able to convert this somehow into where I'm looking at it in kilograms per liter. 999.98 kilograms per meter cubed. Okay, the first thing that you need to do is you need to be able to convert it to something that we can work with. Now, we've actually worked with centimeters cubed before. Okay, so what I need to do is I need to go from meters cubed to centimeters cubed, and here's how I'm going to do that. I know that in one, let me go ahead and make a little room here real quick. I know that in 1 meter there are 100 centimeters. Okay, the problem is that I have 1 meter cubed. So what I have to do is I have to cube everything. And what I do to the top, I need to do to the bottom, so I need to cube everything. So in order to get the units to cancel out, I'm taking 1 cubed and meter cubed. Well, that doesn't affect it in this particular case, but when you do 100 cubed, that makes a little bit of a difference. 100 cubed is actually 1,000,000. So we have our conversion to centimeters cubed, and you're thinking, well, why did I do that? Well, because remember, we have 1 centimeter cubed is 1 milliliter. That's a conversion factor that you should remember from the beginning of the year. If you didn't, you're reminded. Now, the last part of this is you can say 1 milliliter equals 1 liter. Now, if this were the case, that molarity of a substance equals molality of a substance, you would have 1 kilogram equals 1 liter. And if you do this, you do the math, you cancel everything out. Hold on, I should have had 1,000 mils right there. This is going to end up simplifying to the point where you have 0.99998 kilograms is equal to 1 liter, which you can see why many textbooks say this. This is basically 1 equals 1. But depending on the accuracy or the precision of your experiment, that little difference in mass could make a difference. And also, if you see, based on the temperature, it's going to get even worse. Okay, if you increase the temperature to a certain amount, all of a sudden your density factor goes off quite a bit more. So there are some circumstances where molarity is going to be more important, some where molality is going to be more important. We will tend to use molarity though. The maximum amount of lead the EPA allows in drinking water is 0.015 parts per million. It says express this value in molarity and molality. So we need to explore this term of parts per million. And what it means is it's talking about it in terms of mass. Parts per million means that the mass of the solute divided by the mass of the solution or the solvent needs to be very, very, very small. In this case, it needs to be 1 times 10 to the sixth. So when you talk about parts per million, it needs to be times a million. Okay, so when we look at it in this particular case, you couldn't see the 6 because there. Okay, so now if you were to take a look at this, we were given 0.015 parts per million. So 0.015 parts per million equals the solute divided by the mass of the solvent, and then you have the mass that you can have for this particular particle. So when you or times 10 to the sixth. So when you take this and you divide both sides by 10 to the sixth, and then you assume that the solvent is just 1 kilogram, what you end up with is you end up with a mass of approximately 1.5 times 10 to the negative eighth kilograms, and that's in 1 kilogram of solvent. So this right here represents the molality. Well, it's almost the molality. We're in the kilograms right now. So what I need to do is I need to be able to convert kilograms of lead into moles of lead. So we can start that up here. We can say I've got 1.5 times 10 to the negative eighth kilograms of lead, and we draw our lines. Okay. The first thing we need to do is say that 1 kilogram is 1,000 grams. It's 1,000 grams. And then the next thing we do is we say 1 gram is, 1 gram is approximately 207.2 moles. So we got 207 point, scratch that out, 207.2 grams is 1 mole of lead. So once we have 1 mole of lead, and we can multiply this out, and when we multiply it out, we figure out that the moles of lead is about 7.24 times 10 to the minus 8th. So you have 7.24 times 10 to the minus 8th moles of lead. Now remember, we had our 1 kilogram of solvent, so we can say that the molality is 7.424 times 10 to the minus 8th is the molality. Now, we could do the exact same thing for molarity. We should know that 1 kilogram of water is approximately equal to 1 liter based on the example that we did before. Now, is it exactly it? No, but it's pretty close to the point where it's not going to matter. So once we figured out the molarity is the same value. And the reason why I know that is because of 1 kilogram is roughly equal to 1 liter. In this last example, it says how many grams of copper sulfate are required are in 250 mils of 0.250 molar copper sulfate. So the first thing we need to do is we realize that molarity is equal to the number of moles divided by the volume. And I'd say I've got 0.25 as my molarity, and I'm trying to solve for the number of moles, and I have 0.25 liters. So when you do this, you end up getting the number of moles is approximately 0.0625. Now remember, this is moles of copper sulfate. So moles of copper sulfate. Now I can do my dimensional analysis, and I can say that you have 1 mole of copper sulfate, and that 1 mole of copper sulfate has a mass of about 159.6 grams. Now the way that I got that, and you should be familiar with this by now, is that this value right here, this copper, comes from the periodic table is 63.5. The sulfur is 32. The oxygens are going to be 64. There's 16 each, but there's 4 of them. So now when you multiply this out, you end up getting a mass of copper sulfate required to be about 9.98 grams of copper sulfate, CuSO4. Okay, next we need to talk about solubility. Solubility is the amount of solute that can be dissolved in a substance, and it varies depending on the substance. Okay, something is considered to be unsaturated if you have less than the maximum allowable amount of solute. Okay, so if you have less than the maximum possible amount of solute, the solution is said to be unsaturated. A saturated solution is at the maximum allowable level of solute. And a supersaturated solution is when you are above that maximum level. And you may be asking yourself, well, how can you be above the maximum level? Well, there are certain things that you can do to affect the solubility of a solution, like we saw, or like we talked about earlier. If you were to heat up a solution and then dissolve as much as you can and then cool the solution was considered to be supersaturated because it was above its normal values. And a lot of times that results in this. You see crystal formation. Okay, I had so much in the solution that when I cooled it back down, it could no longer be in solution and it creates crystals. So, factors that affect solubility is number one, the temperature. Okay, as you increase the temperature, you increase the solubility. Okay, well, that actually is twofold. You increase the solubility of solids, okay, like sugar, salt, those sorts of things. But as you increase the temperature, you actually have the reverse effect on gases. You actually decrease the amount of gas that can be in solution. So if you increase the temperature, that's why Coke or Sprite or something like that that tends to get hot isn't as good because it doesn't have as much carbonation in it. Pressure, as far as increasing the pressure really doesn't have any effect on the solids, okay, like dissolving a solid in a liquid or anything like that. It doesn't really have much of an effect because solids and liquids are generally incompressible. But if you increase the pressure, you can increase the amount of gas that is dissolved in solution. That's why cans tend to be done under pressure. So whenever you have the increased pressure, you get more bubbles in solution. Okay, the fact that it's a higher pressure than the atmosphere. When you take the cap off, you're equaling the pressure with the outside, and that's why you tend to lose some of the bubbles whenever after you've opened a Coke. So if you increase the pressure, you actually increase the solubility of gases with no effect. You have no effect on solids. And then last is the nature of the solvent and solute. So you know if polar and non-polar and non-polar, like dissolves like, and so you've got to look for those factors as well. One interesting side note that kind of goes along with this idea of solutions is the fact that the solution, the solute can affect the solvent itself. And you get something called freezing point depression. If you put water, okay, this Prestone, this antifreeze, is composed of 50% water. If you were to put it in your engine and it was to freeze outside, your car is not going to, the engine block's not going to break because the water's not going to expand and break everything. The reason why is by mixing it with the glycol, the ethylene glycol, what we've done is we've actually lowered the point at which it will freeze. So whereas normally you have water that freezes at zero, as you start to add a solution, in this case when we add salt, it actually decreases the temperature to, when you have molarity of 10, the freezing point of the water solution is now negative 20. That's the primary reason why they salt the roads. The salt isn't there to provide traction. It can help in providing traction. But by adding the salt to the ice, you actually decrease the freezing point. So instead of it being at 0 degrees C, it's now negative 20 C. And so it actually has the impact of melting the ice. Well, likewise, you can have something called boiling point elevation. So just like you can decrease the temperature at which water freezes, you can actually increase the temperature at which water boils. And so this right here is the same thing. It's the reason why you add salt to boiling water before you cook the pasta, and it shortens the time that is required for you to cook it because you've increased the temperature from, let's say, 100 degrees Celsius to something like 110 degrees Celsius. Because of that, it does not take as long for the noodles to cook. Now, it says different areas of the country have different mixtures of antifreeze for use in their cars. Determine the appropriate level of ethylene glycol for 5 geographically distinct areas. So if you look right here, down here in maybe San Antonio, it's very hot. And so since it's very hot, you have no real need for a large portion of ethylene glycol to be in your car's antifreeze. So you'd be looking at something like maybe this, maybe 20%. Because at that 20%, it would protect you if it ever got below freezing, which is unlikely to occur. But if you were to look at other areas, like let's say Let's look at Dallas right here. Dallas is more likely to be cold, so might want to increase the percentage of ethylene glycol to be about 40%, so that we're more protected in case it gets very cold. Now, the points at which you're trying to look at that are the absolute coldest, you're looking at right here in northern Minnesota and maybe the upper part of Wisconsin. But that right there is where it gets very, very cold. The average temperature is 40 to 50 degrees Fahrenheit, which means that it can get very, very cold during the winter. So at that point, you might want to start to look at something like this as far as 65, 70% ethylene glycol, which means it would make it much less likely for a car's engine to freeze because you've decreased the temperature to negative 50 degrees Celsius. A solution is confined to a fixed container. What can be done to increase the solubility in this particular container? So if you're to look, there's a couple of things, and it matters. Number one, you have to define the solute. What is the solute? Because it matters. If the solute is a solid, there's a couple of things you can do. You could increase the temperature, okay, but that would be kind of tough because the can could, you know, uh, expand and then potentially break. But if the solute is a gas, you could decrease the temperature, which would be nice, or you could increase the pressure that's on the can. Those are the two options you have, but it's kind of a difficult question to answer because you don't know what the solute is, and that's the purpose of this question. Until you define the solute, you don't know what you can do to increase the solubility. All right, soluble, insoluble, or somewhere in between. So earlier we classified substances as being insoluble, saying that they wouldn't dissolve at all, or soluble, which means that they would. But in reality, there's a continuum. You have things that are soluble, and you have things that are insoluble, and there's a whole lot of gray area in between. In fact, even these will dissolve things slightly. So what is really insoluble? This right here represents a solution of lead. I think it's lead nitrate, and that solution of lead nitrate, it looks like it's got some sort of lead nitrate dissolved in water. But it turns out if you let it settle to the bottom, most of the color comes here, but there are still flakes of yellow that are in the solution. So there is some degree of solubility. So when we want to look at the difference between the solubility, we have to introduce a new concept, and that concept is the idea of the solubility product. Before we go any further, I want you to go ahead and cross this out and realize that these were backwards. These are supposed to be C over C, D over D, and on the bottom is supposed to be A over A, and B over B. Okay, so you just flip what was there. What you do for a KSP expression is you take the products and you divide it by the reactants, and that equals a special value called the solubility product. This is a constant value that will tell you how easy it is for something to dissolve. Actually, we'll take a look at it a little bit later in acids, and we'll say the ability of an acid to disassociate. And that's really what this is. So you generally get this KSP value from a table. And if you look, you have these KSP values on the table. The smaller a KSP value is, the more insoluble it is. Okay, I know that gets kind of confusing. Okay, the lower the KSP value, the less soluble it is, or the more insoluble it is. So it is going to be very, very difficult to get aluminum hydroxide to disassociate. Okay, it is going to be much, much easier to get lithium carbonate to disassociate. Even though both of those, well, lithium carbonate not really, but carbonate is generally considered to be insoluble. But even so, there's a big difference between those two. So we're going to get some practice writing these KSP expressions. In this example, you have 200 grams of silver iodide and 200 grams of silver 1 chloride that are added to separate 1 ml volumetric flasks, and then water is added to the mark. So we've made solutions of them. Now the question is what is the concentration of silver ions in each? So the first thing that we need to do is we need to look at the idea of, we need to find the KSP values for each of them. So in order to do that, we refer to the table, and when we refer to the table, we get the KSP value for silver iodide. Silver iodide is 1.5 times 10 to the negative 16th, and that's the value for the KSP. When we look at it for silver chloride is 1.56 times 10 to the negative 10th. And you say, well, what does that have to do with anything? In each of these expressions, you're going to have something like AgI is going to disassociate into Ag plus I. Now, when you write the K expression, what the K expression is going to be silver times iodine divided by silver iodine, and that equals the expression for the K value. Now, all of these exponents are 1 because there's 1 in every part of the coefficient. If this was 2, then I would have to change this to 2, but it's not, it's 1. You can do the exact same thing for silver chloride, and when you do it for silver chloride, you get the exact same expression with just a little bit of difference. It's chlorine instead of iodine. Okay, so now this gives us an expression that we have for the KSP value. But one of the really, really important things for you to understand is that solids are not included whenever we look at a KSP value. AgI is considered to be a solid. AgCl is considered to be a solid. So it cancels out in both cases. So what we're left with is just the expression K equals Ag times Cl. And then you also have the expression K equals Agi. So now if I'm trying to figure out the one that has the most amount of silver ions, if you look, none of this really matters in terms of how many grams of each is added. So here's the last thing that we've got. I've got the values. 1.56 times, 1.5 times 10 to the minus, I believe that's minus 16th. Yeah, we missed that 1 right there. It's minus 16th. It disappeared again. There it goes. To the minus 16th equals this. Now, I don't know how much silver I make, so I'm going to represent that as X. But for every silver I make an iodine, so I get an X there as well. And on the other side, you're going to have 1.5 times, this is 10th, 1.5 times 0.56, sorry. These are very close values. Times 10 to the minus 10th equals, and I'm going to have the same thing. I'm going to have the x times the x. Remember, x times x is the same thing as x squared. So you can take the square root of both sides, and that would give you the amount of silver concentration that's in both sides. And if you were to do that, you would get approximately, for silver iodide, you would get 1.25 times 10 to the minus 5th, or excuse me, 1.22 times 10 to the minus 8th. And for silver chloride, you would have something like 1.25 times 10 to the minus 5th. So even though these solutions are very, very similar, they're both Ag, they're just silver with a halogen, and when you combine them together, they have the same formulas, they have the same KSP value, or K equations basically. They have very different amounts of silver that are in the solution based on the solubility product. So the higher the solubility product, the more likely is something to dissolve. Okay, now if we were to look at the next example, it says you have two substances are mixed with water in separate volumetric flasks. The first produces a concentration of 8.78 times 10 to the minus 7th when allowed to ionize, while the second produces 7.6 times 10 to the minus 3rd when allowed to ionize. It says both solutions produce an equal amount of anion. To determine the expression of both of these based on the KSP value. So you're going to have a K value, and it's going to equal, you're going to have silver, and then you're going to have whatever the other halide is. Don't know what it is. But it tells me that they're in equal amounts. So because of that, I can say that the K value is going to be equal to whatever silver is times whatever silver is. Or in other words, silver squared. So that the first one, I can plug that value in, and I can say is equal to 8.78 times 10 to the minus 7th squared. And when you do that in your calculator and you square it out, you get 7.71 times 10 to the negative 13th. I'm going to do the exact same procedure for the other one. I'm going to say K equals, and then it ends up being 7.6 times 10 to the negative 3rd squared. And when you square that value, you end up getting a value of about 5.77. Excuse me, hold on just 1 second. So we got to square that value, 7.6 times 10 to the 13th, or excuse me, 10 to the negative third. And then we square that value. And when you square that value, you get a value of approximately 1.3 times 10 to the minus sixth. Okay, now we have our values. We want to identify what the solutions are. So we have to use these k values that we calculated, and we have to go and figure out what they are. We know that silver's in both of them. So we go to our silver values and we look right here and we say, what are the closest values? Okay, it's not always going to add up to be perfectly right. So let's take a look and do the best that we can. If you look at this one, I have 7.71 times 10 to the negative 13th. And when I go back, I've got 7.7 times 10 to the negative 13th. So I'm fairly confident that when I do this, that the value for this first substance is silver bromide. Okay, for 1.3 times 10 to the minus sixth, it gets a little bit trickier. When you look at it, there's no value that really fits what it actually is. So you've got to look at it and say, okay, was this a cause of error, or was this something that I did mathematically that was wrong, or was there something wrong with the measurement? If you were to look, the closest thing would be this. And you look, how is 5.77 close to 1.3? And the reason why it's different is you have this idea that it could be twice as much. But what more likely occurred is there is an error in the measurement. So that's something that you have to take into account whenever you do these values. You've got to say, does it match something? If not, what is a possible source of error? And in the last one, it says write a KSP expression for the ionization of lithium phosphate in solution. So you have lithium. Phosphate is this right here. It's going to ionize in a solution to 3 lithium and 1 phosphate. So when you write the KSP expression, it's going to be K equals, we don't know if this is aqueous or not. We're just gonna say that it's a solid because, well, we'll call it aqueous so we can see what it is. So this expression would be Li 3 PO4 1 divided by Li 3 PO4 1. Now, if it turns out that this lithium phosphate ends up being a solid, all we have to do is take it out of the expression. This is a tough ending to it, so make sure you bring lots of questions when you come into class so we can go over and make sure everybody understands this.